Hello to everyone. In today's video, we are going to be looking at the first order linear differential equation. And a linear differential equation, especially a first order, is a differential equation of the form dy dx plus p of x cure equals to q of x. Now, here we have to look for what we call the integrating factor, and after getting our integrating factor, to get our solution of the differential equation, we simply multiply our integrating factor by y equal to the integral of I q of x dx. So basically our q of x is the same as the one that was here. So now, without much to do, let's jump right into our first example. Now, this is our first order linear differential equation. Now, to express it in this form, what we need to do is we divide all through by x. So here, if we divide all through by x, we divide all through by x, we divide all through by x, then we're going to have our dy all over dx minus, let's say plus minus 2 all over x y equal to x cubed. So if we want to compare this with what we initially have, we know that from the general formula we have dy dx plus p of x y equals to q of x. So it means clearly here that our p of x will simply be equal to minus 2 all over x, and our q of x will simply be x cubed. Now, to get our integrating factor I, will simply be e raised to the power the integral of p of x dx. But we know that our p of x is negative 2 on x, so this will be e to the integral of negative 2 all over x dx. Since negative 2 is a constant, we can send that out, so this will be e to the negative 2 the integral of 1 all over x dx. So that we'll have e to the negative 2 the ln of x, so that this will result to e to the ln of x to the minus 2. So from here we're going to have minus 2 as our solution. We're going to have x raised to the minus 2 as our solution. Yeah. So now, to get our final solution, we're going to multiply our integrating factor with the integrating factor. Means our integrating factor is x to the minus 2. So we're going to have iy equals to the integral of I cure of x dx. So basically we are going to have y times x to the minus 2 to be equal to the integral of x to the minus 2 times q of x. Q of x was x cubed, now is dx. So pardon, we have dx there. So here we have our y x to the minus 2 to be equal to, we're looking for the integral of, so from indices and logarithm we have to add this, so we have it will be x dx. So we have our y x to the minus 2 to be equal to, this will be x squared on 2 plus our constant k. So if we look for our y, this implies that our y will be equal to x to the power 4 divided by 2 plus x squared k. So basically that is our value of y. So if you haven't checked out the part 1, 2 and 3 of the video series, then I'm going to put the links in the description box and also above the video so that you can check that out. Now moving on to the next example, we have our linear differential equation in this form dy dx plus y all over x equals to x squared. So the question has already arranged it in the form that we want. So here we're just simply going to say our p of x will be equal to 1 on x, and our q of x will simply be x squared. So here our integrating factor I will simply be equal to e to the integral of p of x dx, which will be equal to e to the integral of 1 all over x dx, which will simply be e to the ln x, which will be x. So we have that our integrating factor I is x. So we keep that aside. Now, to get our solution, we have iy to be equal to the integral of q of x I dx. So this implies that we have our x times y to be equal to the integral of x squared. So basically it means our xy will be equal to x cubed all over 3 plus our constant k. So our y will simply be equal to x squared all over 3 plus k all over x. So that's our solution. Now moving on to the next example. Now our next example, we have been given um our first order linear differential equation in this form. So here you see that our p of x will simply be tan x, and our q of x will simply be sec x. So clearly we see that our integrating factor I will be e to the integral of p of x dx. So we're going to have our integrating factor I to be e to the integral of tan x dx. So when we integrate tan x can be written as e to the integral of sine x all over cos x dx. So we see that differentiating the denominator, we are going to have negative in the numerator. Therefore, what we can do here is we create a negative sign here and we put another one out. Now, when we look at e raised to the negative, we haven't changed anything at this point. So here our answer will simply be e to the negative, the ln of the absolute value of cos x. So that this will simply end up with 1 all over the absolute value of cos x. And cos is a positive value, so this will be 1 all over cos x. Cos is a positive function, so multiplying by our integrating factor q of x dx, then we are going to have our integrating factor is 1 all over cos x times y equal to the integral of 1 all over cos x, and now q of x is sec x, and our sec x is 1 all over cos x dx. And we know that 1 on cos x times 1 on cos x is 1 all over, so we're going to have y all over cos x to be equal to the integral of 1 all over cos squared x dx. So we can write our cos squared x as sec squared, the integral of sec squared x dx, and the integral of sec squared x is tan x. So y all over cos x to be equal to tan x plus k. I'm going to leave out some exercises. For those who are interested, you can solve and you put your solutions in the comment section. So we have this. This is the first exercise. Mm, this is the second exercise, and lastly the third exercise, and lastly the third exercise, and lastly the third exercise.